Yeah, we're the. We gotta use a full noodle, of course, and we're attempting to we're attempting to approximate the area under the curve. It's an approximation. It's not perfect. You're right. True. I did have to like dip down there to fit this gets in there. And the title of the section of your book is Estimating with Finite Sums. And that picture kind of, I don't know, you could say it kind of sums it up a little bit. Are the math teachers the worst at that? I don't know. I go a little crazy. Let me give you just a frame the lesson just a little bit. We have been talking about the derivative for a lot of time now, and we understand that to be kind of equated, at least informally, with slope, a rate of change. And we're now turning our attention to another subject of study in calculus called the integral. And we'll discover what connections there might be between these two things. It's certainly true that we can now, what do you think is going to go here after our activity? Area. Yeah, we might think of this in terms of area. We're looking for a geometric concept to capture this. Though both of these are slightly impoverished definitions, because obviously we don't rely on the graph of something necessarily to actually think about what it's doing. The slope makes us think about geometry, but we understand that derivative can actually be like all sorts of different things in terms of quantifying a rate of change. Similarly, actually, maybe a better word would be like accumulation here, right? Because a lot of times we're not interested in like figuring out the area of something per se. It's more the amount that's been accumulated by a particular function over time or over some period. So we'll say this, and actually this will become more important later, but this piece here, but the definite integral is in fact, for a positive function, it does actually correspond to the area under the curve, and you've just seen that to be the case. And we'll clean up this definition, this somewhat informal definition, as we move forward. And I do say this here. This is actually a very, very powerful idea. So that's just kind of a way of framing what we're doing here. You've probably heard of differential calculus and integral calculus. Well, here we are. We've arrived. Are you excited about wanting to learn about integrals? Have you heard about, right? You've seen your friends drawing integrals and stuff, and you're like, oh, that looks so smart.
I can't understand.
I want to be like that.
Can't understand.
Yeah, you can't understand anything until you learn. There are a couple methods for finding the area under a function. One of them is geometry, right? Like you could actually, if the curve has nice properties, like I think you can already calculate the area under linear functions without my instruction. Am I right? Yeah. Because if it's not a triangle, maybe it's like trapezoidal underneath. You could kind of you could break it up into rectangles or triangles and get not just like an approximation of the area under the curve like we've been doing just now, but for those types of, for a certain class of functions, you could actually maybe get the exact area under the curve with some geometry using known shapes. The one we'll focus on a lot here is rectangular approximation. And it kind of looks like this, though we'll say some more about it as we move forward. And this is clearly an approximation, but I think you'll learn to like this, and you'll see the reason why we go for that. First of all, we're going to use that for any curves of interest that we have. And the fact that we can come up with a systematic method for doing this means that we can also do this with increasing and arbitrary accuracy. Later we'll also study something called trapezoidal approximation method, I think on Wednesday this week. I'm trying to think where that comes in here. And that's just, can you see the trapezoids? That's just, instead of assuming the function, this kind of makes the mistake of assuming the function is piecewise constant. This one down here kind of makes the mistake of assuming that the function is piecewise linear, right? And you can see where it's this is a drastic overestimate on this particular interval and things like that. So don't get too caught up in drawing those pictures with precision right now or anything. I just want to kind of illustrate where we're heading with some of these ideas. And then there will be actually, eventually we'll give you some algebraic techniques for doing this. Maybe even doing this exactly for any curve. That would be an interesting and powerful thing, huh? again, keeping in mind that these are not just like curves and geometry, this also will be, you know, lots of real world applications. These curves might be cost curves or who knows wider. So, okay. So let's actually try this second thing here, this idea of rectangular approximation with an example, with a little curve. Everybody's drawing. Yeah, Albert, while we're waiting.
How accurate is the rectangular approximation method and the trapezoidal approximation?
I mean, I think generally the trapezoidal approximation method is a little better, but you'll see, you'll see the relationship between these methods as we move forward. We have a couple different rectangular approximation methods, some of which are better, and it depends on the curve too. You could construct a curve for which one is better than the other, depending on how you set it up. But I like that you're already thinking about like which one is going to yield best answers. It's good. So let's think about x squared plus 2, kind of a nice parabola to start us off with. And we'll be approximating the area on the interval, just from the interval 1 to 5. So I think you can picture that here. I've kind of got a skewed, this is very, very finely grained on the y-axis here. So the first thing we're going to do is divide the interval into subintervals. Let's do, for this example, let's actually pick, I have shown here just 3 rectangles, but obviously you can pick as many, that's a choice. And the kind of approximation I'm doing right here is, we're going to call left-hand rectangular approximation method, or just for short, LRAM. And notice that this is the interval 1 to 5, and I'm replacing on each subinterval that I've partitioned this into. I'm replacing, I'm like using, for the area of the curve, I'm representing a rectangle with a height, and what am I taking the height to be? Well, I'm taking it to be the value of the function at the left end of that interval, for each interval, yeah? You see that it agrees with the function at each left endpoint? So that's called left-hand approximation, and it probably goes without saying what right-hand rectangular approximation looks like. Now notice that we can do that with unequal subintervals. It's maybe more natural to do it with equally sized subintervals, and it could look something like that. If you're setting one of these up, you probably might pick equal subintervals. But if you have just data that's been handed to you, you might be forced into having to do this kind of thing, if he actually likes to do that to you. And already you're probably like looking at this with a critical eye. I promise this is a fruitful place to go with this, okay? But right now you're thinking like, that's terrible. Like I could do better counting boxes. True. For now. So then, in general, I've tried to make this a little more abstract here. What is the area equal? Well, it doesn't equal anything. It approximately equals the sum of those rectangles. And I'm just going to start using this sigma notation. I'm hoping that you remember how that works. Now, I know this isn't fully resolved, but all I mean here is I'm adding f of xi, and for each of these, xi is the representative for each subinterval, the ith subinterval. In this case, that'll be like the left-hand endpoint for each of these. All right, so xi will be, in this case, as we iterate up, x1 will be 1, x2 will be 2, x3 will be 3, and x4 will be 4. And we'll evaluate f of those things. And then delta x, in this case, for all of these subintervals, for all of them, will be just 1. Which is a convenient thing to multiply by. I like doing that. Love finding the area of rectangles when their width is 1. It's huge fan of that. And then all I'm just saying is sum them up for, in this case, from 1 to 4 is in this picture what I'm doing. I think you know sigma notation, but that's what's going on there. Again, emphasis on the fact that this is an approximation, obviously. or let's put velocity into the picture here too, giving especially like the example we just did, kind of with the warm up when we walked in, suggested that this might be a good place to go too. Physics is always like a great place to go. So we have a velocity function, and we're actually going to calculate a distance off of this using a technique that we've just been playing around with and I'm abbreviating that to LRAM4. By that I mean 4 subintervals. Again, that's convenient because I'm doing over 4 seconds. That's actually me doing you a favor. Right? There's no reason I couldn't ask for a different number of subintervals just to be strict. And we will. But yeah, Matthew had a question.
Just asking if the notation on the previous slide
Yeah.
with the sum would only work if the intervals would be in space.
Yeah, I made that. I mean, I had the delta x as if it was always the same, but the only thing you have to change is maybe call that like a delta xi or something, where each delta x is different or something, and then you could generalize that formula to that situation. So I have a graph of this: 1/8 t squared plus 1. I'm finding, again, I'm using LRAM, so I'm using the 4 left endpoints here of each of those intervals 0 to 1, 1 to 2, 2 to 3, and 3 to 4. I'm using the left-hand endpoint. I'm drawing these rectangles. Again, I realize this is like a terrible approximation, but we're gonna go with it. And I think if you plug these in, that is the left-hand endpoints for those 4 subintervals. 0, plug in, 1, 2, and 3, plug those in. And see what you get from the original function. These are the values you get. And then if we just sum those up, now again, this is not very exciting because it's just each of these height values times 1 for the width, yeah? So you add those up. Keep in mind, never ever lose sight, because it's very easy to quickly be like, okay, now what's the formula for LRAM? Just never lose sight of the fact that all you're ever doing in these examples is adding up the area of rectangles. Okay, that's all we're doing. There's no like heavy machinery here, even when the notation looks scary. Rectangle, first rectangle, second rectangle, third rectangle, fourth rectangle, down below. And I'm not like super interested in discussing the arithmetic, but it does come out to 5.75 meters, which I think a lot of you have already observed is an underestimate. Now, I'd love to start thinking about systematically about this kind of a left-hand approximation. When do you think that does provide an underestimate for a function we do LRAM? You already have an idea? When it's concave up, try one that's concave down and see if that confirms your or destroys your thesis. Go ahead. When it's increasing, see who's right, figure it out. Okay, draw some pictures. Okay.
It's going to be overestimated.
Okay, yeah, does it have to do, is it as simple as that? Is it just increasing or decreasing? Or is there more to the story? This is the question. Let's think about it as we go on. Let's try, let's also mention some of the other things that can be done here too. Right, with this particular function, we just did LRAM. RRAM looks like this. Notice, in fact, it's the same function values, except for the first one, the first rectangle, we're using the right-hand endpoint, which we used in the other calculation, and then we're finally using the endpoint here too. So we're using 1, 2, 3, and 4 this time, and plugging those into the function. That seems to provide what kind of estimate? An overestimate. What's MRAM? The midpoint rectangular approximation. So just to be clear, that is not like the halfway point between the two y values. It's the halfway point between the two x values, and we plug that in, right? Which is, of course, unless it's linear, is not the same thing, right?
Is it better to use MRAM than LRAM or RRAM?
Yeah, I'd like you to think about that a little bit, and I'd like to also, I don't want to provide too many answers before you like played around with these a little bit to these estimation questions about which ones are better and all that. Again, actually, I think we've started to have a good conversation. It's not super hard to ask whether this is an over or an underestimate, these guys. The criteria has actually been said already. I don't know if you, I want you to come to some conclusions on that. It's a little tricky to figure out what MRAM is, whether it's an over, when that will be an over or an underestimate. But maybe I'll give you a chance to think about that too before we come back to that. So let's do it with RRAM 4 too. I'll just show you what that comes out to. There's the picture. here's the table. Notice the values are the same, except I've not got 0, 1 on the table anymore. And I do have 4, 3 on the table now. So it's really very similar in the mechanics. And you can write this down if you like, but in the end you'll get 7.75 meters. What was the previous result? 5.75. We kind of have like a lower and an upper bound for what the actual value of this integral is. And again, those are not actually very tight bounds on the value of this integral. But something, at least. In this case, it seems to be an overestimate. Let's actually answer the question finally. When is, someone other than Peter and Judah, when is RRAM an overestimate? Or when is LRAM an overestimate? Can you say what's going on there, Rebecca?
So when it's an increasing interval, RRAM is an overestimate. When it's a decreasing interval, LRAM.
Right. Yeah. Okay. And so I think you're agreeing with Peter over here. Are you agreeing with Peter? All right. Sorry, Judah. But your logic might help with some of the other approximation techniques we'll look at. So keep that in mind. The cavity does come into play on some of these others. So it is as simple as, is it increasing or decreasing? If we're asking whether LRAM or RRAM overestimates or underestimates. Now, keep in mind, if it's not a monotonic function, then we don't know, right? Like it could be, who knows whether it's an overestimate or underestimate if it's like going up and down. But if it's strictly increasing or strictly decreasing, we can pretty easily say which it is. Sorry, was that? Is it good? RRAM?
I see.
I'll just show you MRAM too, but again, this one actually is a little more interesting than the last one because the table is completely different now, right? The table values I'm using are 0.5, plug that into the function. 1.5, plug that into the function. And I didn't write anything as fractions, but I think these are exact values here. So. And of course, you can do the same thing. I didn't even write out the calculation, but there it is. It's 6.625, which does seem to be kind of in the middle of the other two and a good estimate here, better than the others. And in fact, you can kind of even see why. Like this is, like this piece could go here maybe. Like that feels better. I think you might be right. Now, this is a little bit of a tougher one. I'm just going to leave this question hanging, and someone can come back and we'll like hear the answer tomorrow maybe. But I'd love to figure out why. I'll just tell you right now, this is an underestimate. It's a little hard to tell maybe. Maybe you can convince yourself. But I want you to think about why that is. Don't shout it out if you really convince you know. But that's a little bit trickier to figure out why that's an underestimate. So we've now thought about LRAM and RRAM and MRAM. Hopefully you know what those acronyms mean. Let's use the same example just because we love it so much. By the way, we haven't even been paying attention to the unit, because the meters always happens, right? Let's do it with this time. What's the instruction? MRAM 8. What? What does that mean? Well, that means do the same thing, please. Estimate that we're trying to get a figure on the same, we're trying to get an estimate on the exact same figure. But this time we're using 8 subintervals, okay? So that is 0 to 1 with, 0 to 0.5 will be this first subinterval, and if we're using MRAM, its representative value for that interval will be 0.25 then, is what we're plugging in, right? Tell me what you think about how this is going to go. You think that you're going to like this? You like it already, I can tell. Add them up. I'll just tell you, just get that times, now that's actually, what is that? This is the same thing. It seems like we were getting different values there. What's going on there? I just added them up. But what's the width of each rectangle here? Yeah, so we should have multiplied each one of those by 0.5. It's all right, we can do that after the fact. It's 6.65624. That's better. Are you starting to see why rectangular approximation has a way in for us on this problem? Because we can make this smaller and get a better estimate, and we can do it in a systematic way. your dot counting method, like, I don't know if I can teach like a computer to do that, right? Okay, well if you see like a partial box, then do like count one of these, and then like count that as a, I can't, but this I think I can teach a computer, yeah.
Can we do this kind of like Newton's method with the gas?
No, well actually, I mean we can do this for any number of intervals here. But we don't have to start with a guess though. Alright, I'll teach you how to use that program tomorrow. Well, but your homework tonight is, oh sorry, it was on the first slide. I'll put it back to the first slide. I think we don't have a homework sheet for you because there are only a couple homeworks. So you just get to add up some rectangles tonight? Have fun.
Yes, that sounds right.
Do you like rectangles?
Size.
Take a picture. Or, you know, write it down, something.